This is a very short section. It's on the equilibrium constant, and it takes us a little deeper into understanding what's going on. We say here it is stoichiometry dependent. No, kinetics was not. It depended on the experiment. So the equation that I use often, because it has three distinct stoichiometric coefficients, is for the synthesis of ammonia. In the beginning section, we said K will always be products over reactants. If you look at what I've done, ammonia is a product and my two reactants are nitrogen and hydrogen. So what have I done further? Well, I've taken the stoichiometric coefficient and I've used it as an exponent. When we have a 1, we don't write anything down. When we have a 3, we then use that as the exponent. It is that simple. So that would be for any chemical equation, and we try to generalize it here. If there is a group of reactants that go on to form products, the products go in the numerator, the reactants go in the denominator. Hence, P, Q, A, B. Very, very simple. What are the exponents? Well, again, they're going to be the stoichiometric coefficients. So this is a method. I don't know who exactly developed it, but use it, and you can really make some progress in understanding this chapter. Now, K is going to be dimensionless, and why is that? Well, anytime we have a concentration at equilibrium, it represents some molarity. By definition, it is ratioed to a 1 molar concentration. And this again is activity. I'll delve deeper into it in lecture, but for now, please just accept it. What do we have here? Well, remember, there is this double-headed arrow, and equilibrium can be reached from either direction. When I look at the case on the left, notice I have started with green and blue, meaning I have hydrogen and nitrogen. So in this case, I am going in the forward direction from reactants to products, and I do the measurement in the lab, and I see there's a point where equilibrium is achieved, where things level out. What do I have on the right-hand side? Well, on the right-hand side, I have the orange, and the orange represents ammonia. Ammonia is going to go away as the reaction proceeds in the reverse direction. I have products going to reactants, but notice what has happened. In both cases, when I achieve equilibrium, the concentrations are the same. Yes, all of this is conceptual. Please try to say, I guess I'll have to believe it, okay? The other thing is you can change the initial concentrations, and you're always going to get the same value of K. So what are they showing in this table? Well, they ran a series of experiments. They used different initial concentrations, okay? Here we have the N2O4, the NO2. You can see in one case they made it 0 here. For the other case, they made it 0 here. But in the long run, when they did the measurement and took all the numbers for equilibrium, they had the same value. Will it be identical? No, it'll be in the same ballpark because there's experimental error. But we'll teach in the next sections about how to find an equilibrium concentration. The thing to take home here is I can change all the concentrations, but I'm going to get the exact same value of K. Let's see what else is here. Well, we could be working with molar concentrations, but let's say we are working with gases. Notice instead of saying aqueous, I have put a G. And what I have done now, since they are gases, I have used a P. And the spacing should have been moved over a little bit left. But we still have products divided by reactants, and we don't have molarity. What we have is pressure. And again, as you work problems, you got to make decisions. So what can we say about the equilibrium constants? You can relate them, and Kc is for aqueous solution, Kp is for gas reactions, and this is based on PV is equal to nRT. I normally work this on the blackboard, but no one has ever asked you to derive it. What I will do is I will say, please memorize this. I know you get an equation sheet, but if you've got these set in your brain, problem solving goes a lot faster. I usually write it in this form because notice I have a p here, and notice my exponent is a positive delta n. But what are these terms? Well, you can be given a Kc and a temperature and an equation. R, we're going to have to go back to the units for gases. Delta N is going to be the moles of the product as the equation is written, minus the moles of the reactant as the equation is written. So let's go back to our original equation. Dinitrogen tetraoxide going to form 2NO2, nitrogen dioxides. What am I doing here? Well, I'm looking for the delta N only of the gases. I have 2 gases as a product. I have 1 gas as a reactant, and so I come up with the number 1. If I come up with the number 1, what I have here is Kp is now equal to Kc times RT, which is the gas constant times temperature. Should I work it for you? Possibly, but you'll just look at it. So please take the time to do the homework and work through the problems with math. They're going to ask you math questions on the exam, so I have to make sure you're ready for that. The last slide here is a summary slide. What does that equilibrium constant tell you? Products divided reactants. It tells you the extent, but I haven't talked about that yet. We'll know that K has a couple options. It can be greater than 1, K can be equal to 1, or K can be less than 1. That is the next section. They really broke this chapter up very, very nicely. But no matter what K is, it tells you nothing about the speed, nothing about how quickly it's going to reach equilibrium. You need kinetic information. You need to know what is that rate law in order to come up with the speed.